Hello everybody. Today we will talk about two of the algorithms used in public key cryptography. We will focus on RSA and ElGamal. Okay. Before we go to the algorithms in detail, we first discuss in brief about public key cryptography. So this is one type of cryptography which is different from symmetric cryptography in that in terms of the number of keys to be used in the algorithm. So for public key cryptography, actually we will use different keys for encryption and for decryption. So this is different from symmetric cryptography. In symmetric cryptography, we need to use the same key both for encryption and for decryption. There are 6 components of public key cryptography. I think this one, plain text encryption algorithm, ciphertext and decryption algorithm, all are also components of symmetric cryptography, but the difference here is that for the keys, we use 2 keys, public key and private key. So for plain text, that's the input of the algorithm, and then encryption algorithm is the algorithm to transform the plain text into ciphertext, while ciphertext here is the result of the transformation of plain text. And then at the receiver side, we need decryption algorithm, which transform ciphertext back into plain text. And for the algorithm encryption and decryption, we will use 2 keys here, public key and private key. If we use public key for encryption, then we need to use private key for decryption. If we use private key for encryption, then we need to use public key for decryption. So these 2 keys can be used, one for encryption, one for decryption. So we have here a pair of keys. The public key here is made public, so it is known by everybody in the platform, while private key is known only to the owner. This is the illustration of public key. In this case, we use public key encryption. So in this case, we use public key to encrypt the message. The purpose of this scheme is for secrecy or confidentiality. So here, Bob needs to send a confidential message to Alice. Here, Bob will use Alice's public key to encrypt the message. Why he use Alice's public key? Because when the message is encrypted using Alice's public key, then it can only be decrypted by private key of Alice's private key. So nobody else will be able to decrypt the message other than Alice herself, because it is only Alice who owns the private key. So the plain text here is X, and then we can use encryption algorithm here, and it will be the result will be the ciphertext, which is Y here. Y is the result of the encryption of the plain text X using Alice's public key. And then at the receiver side, Alice will decrypt the ciphertext here using her private key. The result will be the original plaintext, which is X. Okay, so this is the first type of the use of public key encryption. The second type is for its use for authentication. Here we will use private key of the sender. Why? Because when the private key is only owned by, in this case, Bob. So if it is really encrypted, if the plaintext is really is encrypted by Bob, then it can be decrypted using Bob's public key. So in this case, the purpose is for authentication, to authenticate that it is only Bob who will be able to encrypt the message using Bob's private key. Yeah, the input here is X, and then using encryption algorithm here, the plaintext will be encrypted using Bob's private key, and the result is Y. Of course, Y here is different from the previous Y here, because here in the first encryption scheme here, we use Alice's public key, while in this case we use Bob's private key. And then at the receiver side, Alice will be able to determine whether the message comes from Bob himself or anybody else, because Alice will decrypt the message, the ciphertext here, using Bob's public key. And this is the result, which is X. Actually, other than Alice, everybody else here who owns Bob's public key will be able to decrypt the message. So the message is not confidential here. So the use here is for authentication, to determine whether it is really Bob who sent the message. There are several public key algorithms such as RSA, Diffie-Hellman, ElGamal, and elliptic curve cryptography. But in this slide, we will only discuss two of them, which are RSA and ElGamal. We will start with RSA here. RSA is an old algorithm. It was proposed in 1977 by Ron Rivers, Eddie Shamir, and Len Edelman. Actually, the name RSA itself is the abbreviation of their last names, Rivers, Shamir, and Edelman. We can consider RSA as the most widely accepted and implemented approach to public key encryption. So up until now, we still use RSA, even though the length of the key should be increased time to time. For this one, we actually based the RSA on Galois field over integers modulo a prime. The exponentiation here takes the pico of logarithm of n to the power of 3 operations. It is a block cipher. So plaintext and ciphertext are integers, should be integers, because we use here mathematical operation. The typical size of n here is 1024 bits or 309 digit decimal. So integers here between 0 and 2 and minus 1 and minus 1 for some n. And the size of n here is 1024 bits. It can be considered secure, because the cost of factoring large numbers is hard. So factorization here takes big O of e to the power of logarithm basis n times logarithm of logarithm basis n operations. So the attack is usually based on the factorization of the large numbers. This is the decryption of RSA. RSA here uses expression with exponential. Then plain text is encrypted block by block. Each block has binary value less than n, and the block size is less than or equals to logarithm basis 2 of n plus 1. The encryption and decryption algorithm is very easy actually. So it is only exponentiation. C here, ciphertext, is m plain text to the power of e modulo n. While m, this is the encryption algorithm. This is the decryption algorithm. The decryption algorithm is just similar, very similar. So m here is c to the power of t. C is the ciphertext. T here is paired with e. So we cannot use e and t just randomly, but they must be related to each other. So m is c to the power of t modulo n. Okay. The sender and receiver must know the values of e and n. So in this case, actually what we use is the public key for public key of the receiver, e and n. Only receiver knows the value of t. So t here is the private key, part of private key. So the public key here consists of e and n, and the private key consists of t and n. In this case, what the purpose of the use of algorithm is for confidentiality, not for authentication. So that's why we use public key of the receiver to encrypt the message. So only the receiver knows the private key, which is related to the public key. That's why the message will be kept confidential until it reaches the receiver. The requirements of the algorithm here, it must be possible to determine the values of e, t, and n. In this case, m to the power of e times t modulo n equals to m. So e times t here must be 1. And then it is relatively easy to calculate m to the power of et and n c to the power of t for all values of m. Then it is infeasible to determine t given e and n. E and n are public key, are components of public key, but it must be infeasible to calculate t based on e and n. For this first requirement here, m to the power of et modulo n equals to m, it will be fulfilled if e and t are multiplicative inverse of modulo cn. Cn here is the Taussian Euler function. So et modulo cn must be 1. E and t must be the inverse of each other. multiplicative inverse. And this holds if T and E are each relatively prime to Cn. Okay, so we will see here RSA scheme. The components here, P and Q. P and Q are two prime numbers. Two prime numbers. It is private and chosen. And then from the P and Q, we calculate N. N here is the multiplication between P and Q, and this is public. Public. So P itself is private, Q is private, but N as the multiplication of P and Q is public. Then we choose E. E is the greatest common divisor of Cn. Cn. Cn is actually this one, Gaussian function of n here. So it is the Gaussian function of n. Yeah. So the greatest common divisor between Cn and E must be 1. So E must be relatively prime to Cn. Yeah, E once again is chosen. Then from the value of E, we calculate T. T here is the inverse of E, modulo Cn. So T here is E inverse modulo Cn. It means that E times T must be 1 modulo Cn. So E times T is equals to 1 modulo Cn. So the private key here consists of T and N. The public key consists of E and N. So private key is T, public key is E. The scheme here is like this. Suppose that P wants to send a message to A. A has a public key here. Public key is published to other parties. Consists of E and N. And then since P wants to send a message to A, then P will calculate the ciphertext. The ciphertext here is M to the power of E. M here is the original message. M to the power of E modulo N. Then it will be sent to A. C here is sent to A. C should be decrypted using his private key. So it is only A who can decrypt the message, because it's only A who owns the private key. The decryption here is just like this. M equals to C to the power of T modulo N. T here is again related to E, in which T is the inverse of E modulo Cn. Yeah, this is the decryption of the algorithm based on Stalling's book. Yeah. So for the key generation here, we select P and key. P and key must be both prime, and P should not equal to Q. P and Q here both prime. Then we calculate N. N equals to P times Q. Then we calculate Cn. Cn is the Gaussian function here of N. Since both P and Q are primes, then Cn can be calculated using P minus 1 and Q minus 1. And then after that, we select an integer, randomly E. The requirement here is that E must be relatively prime to Cn. E must be relatively prime to Cn. So greatest common divisor between Cn and E is 1. Then after that, we calculate T. T is again the inverse of E modulo Cn. So T times E modulo Cn equals to 1. After this one, then we can infer that the public key here is En and the private key is Tn. So we after key generation, then we are ready for encryption and decryption. We use again here the encryption for secrecy. So in this case, we need to use the public key of the receiver here. E here is the public key of the receiver. So for the sender, then what he needs to do is just to calculate C here. C is m to the power of E modulo n. So just this formula to produce the ciphertext C. And then at the receiver side, we will use the private key of the receiver. So m here is calculated based on this formula. C to the power of D modulo n. Yeah, this is an example of how we use RSA. First, we generate the keys. We choose two prime numbers. For example, we choose 17 and 11. Based on that, then we can calculate n. N is p times q. P times q is 187. And then we calculate Cn, Gaussian function of n, which is p minus 1 times q minus 1. And it is 160. We then choose E, choose E such that E is relatively prime to Cn. And it must be less than Cn as well. For example, we choose 7 here. 7 is relatively prime to 160. And then after that, we need to determine T, or we need to calculate T actually, such that Te equals to 1 modulo 160. So T here is the inverse of E modulo 160. From discrete mathematics subject, you already know how to calculate the inverse of a number, the inverse of a number modulo 160 here in this case. So we obtain here T is 23. Yeah, so 23 is the inverse of 7 modulo 160, because 23 times 7 is 161, which is 1 modulo 160. So actually what you need to obtain here is a number in which when it is multiplied with E, then the result is 1 modulo Cn. And again, for the calculation of T, the inverse of E, T here, the inverse of E, then you can see how we do it in discrete mathematics. So based on that, then the public key is 7 and 187, while the private key here is 23 and 187. To encrypt a plain text here, the plain text here is 88, then we need to use this formula. So we just need to do exponentiation here. M here is 80e to the power of E. E is again 7. E is 7 here, modulo n. and the result here is 11. The result is 11. And at the receiver side, we need to decrypt the message based on this formula. So here we use t, c to the power of t modulo n. T is 23, while c here is 11. C is 11, and then t is 23. So it is 11 to the power of 23 modulo 187. And the result is, of course, should be 88, the original message. Okay. This is the illustration of the algorithm. So in the sender side, we calculate here 88 to the power of 7. Again, 7 here is the component of public key, modulo 187, and the result is 11. And then at the receiver side, we need to use the private key. Private key here, 23 is the inverse of 7. The inverse of 7 modulo Cn. Cn is 160 in this case. 11 to the power of 23 modulo 187, which is 88. Yeah, and in real world, actually, of course, the number is not that it's not small. Yeah? So, for example, here we have this message. Yeah? The message here is in text. Yeah? So first we need to convert the message into numeric format. Yeah? This is one of the example. Actually, we also can use other conversion procedure. Yeah? In this case, each letter here is represented as an ASCII character, and then we convert the string to bit array, and then the bit array to a large number. So attack at down here becomes this large number. Then we generate the keys, public key and private key. First, we need to pick two large primes, P and Q. This number must be random and not too close to each other. We use here, for example, Rapin-Miller primality test to generate the numbers. Actually, we generate a large number, random large number, and then we do Rapin-Miller primality test to check whether it is prime number or not. Yeah, and this is P, and this is Q. As you can see here, this is very large numbers. These are very large numbers. Yeah, and then based on P and Q, we are able to calculate N and Cn. N here is just the multiplication of P and Q, while Cn is multiplication of P minus 1 times Q minus 1. Yeah? So Cn here is again the Gaussian function of N. So we will get this again large number. Next, we need to determine, or we need to choose the public key. For example, here the public key is this one, and the requirement here is that it must be relatively prime to Cn. So this is the public key. To calculate the private key, we can, for example, use the extended Euclidean algorithm, like what have been discussed in discrete mathematics. The result here is this number. So the inverse of this is this one, very large numbers. And then for the encryption, we just do exponentiation of the of the message here to the power of t modulo n, and this is the result. This is the result. For the decryption, we just use the formula exponentiation of this one to the power of t, to the power of t modulo n, and this is the result. The result here should be the same as the plain text. The plain text here is this one. Okay, so in real world, once again, we have to use large number for both P and Q. Okay, for the security, there are two types of attack, brute force attack. For brute force attack, then the defense is that we need to use larger key. But the longer the key, then the slower the process will be, especially since we use exponentiation here. If we use large key, then the calculation of the exponentiation will be very long. So the computation time is high. And then the next one is mathematical attack. There are in this case, what the attacker do is to try to factorize n into two prime numbers. N here is known, it is public, so what the attackers want to do is to factorize n into two prime numbers so that P and Q can be calculated, and Cn as well can be calculated as well. From this one, then T can be calculated. For the security, the algorithm founder suggests the rules of P and Q. So the length of P and Q differs only a few digits. For example, here, for 1024 bit keys, P and Q must be in magnitude of 10 to the power of 75 to 10 to the power of 100. So P and Q must be between these two. Then both P minus 1 and Q minus 1 should contain large prime numbers. Then the greatest common divisor between P minus 1 and Q minus 1 should be small. At the moment, actually, we need to use 2048 bit of key, bit key of RSA. Yeah, and this is the illustration of progress in factoring. So from this number of decimal digits, to this one, then 155 as of May 2005. We have here the number of decimal digits 200, and the approximate number of bits is 663. But at the moment, the time taken to factoring is not known yet. But as we are facing with, the quantum computing technology is in progress, then RSA in the near future, when quantum computing is already available, then it is not secure anymore. And then for NIST, actually they already recommend the use of 2048 bit keys for RSA at the moment. It will be sufficient up until 2030, but beyond that, then we need to use 3072 bits of key. So the length of the key is increasing more and more large key, large number of key that need to be used here. Yeah, so this is very large number, 3072 bits. Okay, and if we want to do encryption, which strength is as much as 256 bit of symmetric keys in AES, then we need to use 15,360 bit of RSA keys. So it shows that actually a symmetric key for confidentiality is much more efficient than public key encryption, because here we only need to use 256 bit of symmetric keys, compared with 15,360 bit of public key encryption. Yeah. Okay, now we will discuss ElGamal crypto system. ElGamal crypto system here, published in 1984. It is used in several standards, digital signature, and also in S9. For this one, the scheme is like this one. Yeah? So we use here discrete logarithm, which is discussed in other topic. So first we use Q prime number, then alpha. Alpha is a primitive root of Q. For the primitive root, then you need to see the video related to number theory for public key algorithm. And then for the key generation by Alice, we need to choose random number XA. XA must be less than Q minus 1. Then we calculate, still we use exponential here. YA is alpha to the power of XA modulo Q. And then the public key will be this one, while the private key is X. So Y is component of the public key. Public key consists of Q, the prime number, then alpha, primitive root of Q, and YA itself. The encryption by Bob using Alice's public key. So again, the purpose here is for confidentiality, in which the sender uses the receiver's public key to encrypt the message. Yeah. We select here a random integer k. K is less than Q, and then we calculate k. K is this one, YA to the power of k modulo Q. Yeah. This is a random integer once again, and then K here is different from the capital K here. Yeah. So capital K here is YA to the power of lowercase k modulo Q. Then we calculate C1, alpha to the power of k modulo Q, and then C2, k times m modulo Q. The ciphertext here will consist of C1 and C2. For the decryption by Alice, then Alice needs to use her private key. The ciphertext here consists of C1 and C2. Then Alice needs to calculate capital K here. Capital K here is the same as capital K here, but instead of using the public key, Alice needs to use her private key, which is XA. Yeah. So K is CA to the power of XA modulo Q. And then the plain text is this one, C2 K inverse modulo Q. This is also, ElGamal is also a block cipher, yeah. So each block size equals to an integer less than Q. And then K here, capital K, which is based on lowercase k, is actually a one-time key. One-time key. It is added for additional security of the algorithm. The information about K can be obtained from C1, and then the message M here is encrypted using K to produce C2. Yeah, as we can see, K actually can be calculated by the receiver, not based on the public key of Alice, but based on the private key of Alice, private key of the receiver, C1 to the power of XA. Yeah, and then using K, plain text can be calculated. So at the receiver side, actually there are two steps. The first step is to get K, capital K, and then the second step is to decrypt the message itself. So in this case, the message is M. The message is M here. If we restate ElGamal algorithm, in other words, then we can use these steps. Pop generates a random integer K, lowercase k, and then pop generates a one-time key K using Alice's public key components, YA, and then Q and K, and lowercase k. Then pop encrypts K using the public key components alpha. So the result will be C1. So C1 here actually is a kind of hint, so sufficient information for Alice to recover capital case K, the one-time key K. Then pop encrypts the plain text M using K. Then Alice recovers K from C1 using her private key, and then Alice will be able to calculate the original message using the inverse of K to get a plain text from C2. So C1 is actually not part of the message itself, but it is sufficient information for Alice to recover K. But the message itself is contained in C2. C2. This is an example of ElGamal. So we first use Q here. Q is 19. And then primitive roots of 19, there are many. We choose one of them, for example 10. And then Alice selects XA. XA is 5. So XA5 here is Alice's private key. Based on that, then Alice will be able to calculate YA. YA is alpha to the power of XA, 10 to the power of 5 modulo 19, which is 3. So the private key of Alice is 5, while the public key consists of Q, which is 19, and then alpha, which is 10, and YA, which is 3. Bob here wants to send a message M. M is 17 to Alice. So Bob selects K. K is 6 here. K is 6. Smaller case K, random number. And then based on that, Bob will calculate K, capital K here, YA to the power of smaller case K, modulo Q, which is 7. And then C1 will be able to be calculated using this formula. C1 again is the information for Alice to recover capital K. the one-time key. And then C2 is where actually the plain text the plain text lays. So C2 here is k to the power k times m modulo q. It is 5. So C2 is used by Alice to recover the original message M. Okay, and then Bob sends the ciphertext consists of two, yeah? C1 and C2, 11 and 5. At the receiver side, Alice will be able to decrypt the message. First, Alice needs to calculate K, yeah, based on C1 using her private key XA. Yeah. So the result is 7, and then K inverse is calculated using in Galovit 19, and the result is 11. Then after that, Alice will be able to reduce M. M is calculated based on C2 and the inverse of K. Capital K is 5 times 11 modulo 19, which is 17. Yeah. The security here based on the difficulty in calculating discrete logarithm of YA here. And to calculate A's private key, an adversary must calculate XA here. To calculate the one-time key K, then an adversary must determine the random number with K is again discrete logarithm of C1. NIST now recommends the use of 2048-bit keys for discrete logarithm based public key algorithm. So it is also similar to RSA. If security is required beyond 2030, then the key length should be 3072 bits. Yeah. So again, for this public key algorithm, then we need to use very large number of key, yeah, 3072 bits. Yeah, the slides and everything here is based on the book Cryptography and Network Security by William Stallings. I think that's it about RSA and ElGamal algorithm, two of public key algorithm which we know today. Thank you for watching, and we will discuss again other topics related to cryptography in next videos.